Pleasure to introduce the first speaker of this afternoon, Professor Terry Gaffney, who is going to talk about an approach to the Whitney Equisingularity of complete intersections with non-isolated singularities.
Thank you, Abramo. I would like to thank the organizers for inviting me to speak to you on this topic because it's one of the main threads of my professional life. So in this talk, I want to return to the problem of the Whitney equisingularity of families of sets. And so some past work I did was looking at families of complete intersections with isolated singularities. And that appeared in the Invenciones in '96. And then hypersurfaces with arbitrary singularities, families of hypersurfaces with non-isolated singularities. And that was done with my student, Robert Gassler, and appeared in the Journal of Algebraic Geometry in '99. And then more recently, there is work on determinantal singularities. The isolated case with my student Rangachev. And the essentially isolated case, EIDS, essentially isolated with one of my other students, Ruas. And these are both on the archives. And this one should be appearing any day now on the proceedings of the AMS. OK. So to fix some notation, I have this board over here. This is similar to what Tiago used this morning if you went to his nice talk. So this is my family of sets. These are that's the fiber over 0 of the family. I'm thinking of my sets as being contained in Cn. And I'm thinking of Y, which is the base of the deformation, as being also included in Ck cross Cn. Here we're identifying Y with Ck. This denotes the ideal that defines Y in Cn cross Ck. And this is fixing some notations about the maps that are defining my families. And we have the Jacobian module, the relative Jacobian module. And my notation is that M bar denotes the integral closure of M in OXP. I want to assume that all of my sets and the fibers are equidimensional. OK. So now I want to have some background on Whitney equisingularity. So WE abbreviates Whitney equisingularity. And we have a definition for a start. An analytic space X in our setup over there is Whitney equisingular. If X has a Whitney stratification, with Y as a stratum, so the problem that I want to think about, and I've been thinking about this for a long time, we want to find invariance of the fibers So we want to find these invariants such that their independence of y is equivalent to Whitney equisingularity. And so today I want to combine ideas from these three papers to show you how you can use the combination of ideas to give you some idea of how you might approach this case. And it's most completely worked out in the case where each xy has a curve of singularities, so a one-dimensional singular set. Okay. So let me continue with the background. There are a few theorems that are very helpful in understanding the framework in which we're operating in. So theorem 1 appeared in the Invenciones in '93. And this theorem says that if you have the smooth points of a family, then these pair of strata satisfy W if and only if the partial of f with respect to yi for all I do that over here, is contained in the integral closure of the ideal that defines y times either the Jacobian module, well, the relative Jacobian module of f, if and only if the same thing holds true for the entire Jacobian module. So the reason I do this is that I can work interchangeably as far as Whitney Equisingularity goes with these two modules. Okay. And the excitement about this result is that because the notion of integral closure is basically an algebraic notion, it gives us a way of describing the Whitney conditions algebraically. All right, so I would like to connect this notion, this form of Whitney equisingularity with some geometry here. So I want to assume that the generic rank of M is a module here. M will always be a module. Well, almost always, on each component of a set X is E. So generic rank just means the rank of a matrix of generators on a Zariski open set. And then we have the conormal modification of X by M. In algebraic terms, this is the progen of the Riesz algebra of M. In geometric terms, you can think of this as the closure of the set of pairs, the H, where P is contained in XD, where the rank of M is G. E. The rank of M is E. And H is contained in the projectivization of the row space of M at P. So you pick a matrix of generators, because it's a matrix that has a row space, you projectify that. This is going to be a hyperplane, which is, comes from that row space. Okay, so then the theorem 2 is due to Kleiman and Torup. And this was published in the Journal of Algebra and 94. So supposing we have the following situation. We have M contained in N, contained in some free module, F a free OX module. And we already know that M bar and N bar are close. They're equal off some set V. And X has to have dimension D here. Now, one thing I left out, I realized, is I didn't leave room to put in the map here. So the map is called C, and it projects the conormal modification to X. So anyway, these are equal off V unless C inverse of V, well, I need to say the dimension, unless the dimension of C inverse of V is maximal. And maximal in this context means D plus E minus 2. So unless this happens, M bar is equal to N bar. So it says if we can control the conormal modification of M, X by M, then if we can do that, then we might have a shot at showing that we have this kind of integral closure condition happening. So I want to introduce a tool that's used to test and perhaps control the conormal modification of X by M. Okay. So I want to talk about the polar variety of a module. Well, first off, it's denoted by, we're talking about codimensions, so I subscript here. What I want to do is I want to take the intersection of the conormal modification with enough hyperplanes which are generic with respect to the intersection. And the number I have to take is E minus 1 plus T. And then I have to project it down to X. Where do we get this number from here? Well, because the generic rank is E, the generic fiber dimension is E minus 1. So we have to cut that out first. And then this is going to give us something of codimension T when we project down to X. Okay. And then the corollary is, suppose xd plus k is a family of sets over y, and if m bar equals n bar off v and y, where this is a proper inclusion, not equal, then if the polar variety of codimension d of m is empty, then m bar equals n bar. Okay. Now, the proof of this is easy enough that I can actually give it here without any problems. So we just think what it means for gamma d of m to be empty. Well, this is going to be true if and only if the dimension of the fiber over 0 in my family, well, it has to be small enough that I miss it with my d plus e minus 1 hyperplanes. It's got to be less than that number there. Now, the dimension of C inverse of V then, well, that's got to have a bound. This has got to be less than the dimension of the fiber, or the possible upper bound for the fiber, plus k minus 1, because V is proper. It's not equal to k. And then this adds up together to give me d plus k plus e minus 2. Aha! Well, the magic number that comes out of the Kleiman-Torup theorem is d plus k plus e minus 2. And we have something which is less than that. So that's it. M bar equals n bar. Okay. So this is a good start. And then I have a further remark that we are going to use. If I was just using the machinery so far, I would have to look at each family, and I'd have to try to calculate the polar curve in the family. That's not so good. I want something that depends only on the fibers. I don't want it to depend on the total space. So instead, we have this trick. So this trick first worked with the family of Isis, so that's what I'll state it for. Oh, actually, I'm jumping ahead here. Oops, sorry about that. So this remark comes much later. Sorry. We'll get to that then. Okay. So I want to talk about a family of Isis first. Families of Isis. And then we'll get to that remark. So think about x0, as usual, contained in Cn. Is an Isis. X equals f inverse of 0. And I guess I need to know that f maps Cn0 to Cp. Okay. So let capital F of u and z be equal to f of z plus summation ui vi, vi a basis for OXP mod the Jacobian ideal. Because this is an Isis, I know that actually this is there's a finite number of these VIs, and so this is a well-defined object. And if we look at capital F inverse of 0, then this defines a versal deformation. and it's over the space C tau, where this sum went from 1 to tau. Okay. Well, it has the property that if I take any deformation of f, I can view it as being isomorphic to a deformation that comes by pulling something back from here. And we'll say a little bit more about that later on. So what we can do is make the following definition. And this first appeared in my topology paper in '93, and you can read about it there. So we're given xd, Germ at 0. We're given v, reversal deformation, d plus tau, going down to c tau. Actually, maybe not tau, maybe just k. Maybe we just want any versal deformation. It doesn't have to be the many versal deformation. Okay. Then what happens is this. We define a MD the codimension D polar multiplicity to be the degree over the base of the projection to the base restricted to the polar variety of codimension D of the relative Jacobian module of V. So notice that this just depends on x. I'm not thinking of x. Well, in a way I'm cheating because I'm thinking of x as sitting in a universal family. But because it's a universal family, somehow the dependence on the family disappears. And it depends only on x. Okay, so then I can come to this remark that I jumped ahead to before but didn't finish. Given x a family of ices, we can embed the whole family into a versal deformation. And then MD of x of y at 0 independent of y well, this implies that the projection of V restricted to this polar variety of V, but I'm going to restrict this polar variety of V to x. This is the degree of this projection in the total space at each point here. Now I'm just restricting to what's happening along here. Since the degree is constant, this is 1 to 1. And then that implies that actually the polar variety of the family here, well, let's see, JMZ, huh? That's better. Well, let's see, it's going to be 0, comma y is empty. This is 1 to 1 when it projects down. It just projects down to the singular locus. It projects down to y. And that is it. So we can use this trick to control the polar varieties of codimension D in a family. Now I want to talk about a general framework for doing that, and then we'll get to finally, in the end, the applications I want. I want to talk about sections of analytic sets. So the setup is I have F mapping CQ0 into some smooth M smooth. And sigma is a closed set contained in M. Sigma has a Whitney stratification, minimal Whitney stratification. And say G, sigma is equal to G inverse of 0. And I want to assume that if I take G and compose with F, then this defines F inverse of sigma with reduced structure. Okay. So I need another important definition. Fs is a stabilization. So F has to be a deformation of F. Such that Fs is transverse to the So the Whitney stratification consists of sets Si, and this is going to be transverse to those. And I forgot to mention this too, but we're assuming that F is transverse to the Si, except possibly at 0. So we've already made F very nice, except at 0. And now with this stabilization, we produce something which deforms to F, which is nice for everywhere, as long as S is not equal to 0 here. Okay. Now there are some lemmas that I do not have time to prove today, but which you can find. You can essentially find the proofs in the EIDS paper. I will say words about why one part is true. So now I have will be some notation here. I will call this ED of x, and it's going to be equal to the sum of the multiplicity of a pair of things. So this is F inverse of sigma. Okay. This is the variety I'm interested in. This is its Jacobian module. And now here, I want to look at the other element of the pair is going to be the pullback of the Jacobian module of sigma by F. And this is defined, And furthermore, we have as true that MD of x, which I define using the stabilization, is just equal to ED of x, which I just defined, plus the image of F intersected with the polar variety of codimension d of sigma. So these quantities are intrinsic. This depends just on the fiber, as does this quantity here, although it's not clear how you can compute them so well. In the paper with Rangachev, we computed this in the case where we're working with determinal singularities, and these are matrices of rank less than the maximal, which is n or p, depending on how everything's set up. Okay. Okay, so now I want to talk about the applications here. Well, the first application is already on the archive. That's the one with Ruas. Here we have FSCQ going into Cn plus k. Right. And then sigma, well, sigma is going to be the, so sigma will take as sigma t. And these are matrices whose rank is less than t. So in the EIDS case, and that's exactly when F is transverse to all the strata that appear here, except possibly at 0. And so you have this nice formula for the MD. And then because of the transversality part, you can then show that this produces Whitney equisingular families. Well, you have to do a little bit more work, sometimes a little bit, but this is roughly what happens. The second application is the one that's in the title. So let's work on that. So here I'm thinking about X is the germ of a CI, where the dimension of the singular set of X is 1. Okay. I want to try to capture X as a section of a universal set. That's what I have to do. So how do I do that? Well, what I do is I choose L, which is going to map Cn 0 to C0, L a generic projection for X. This just means in this case that L inverse of 0, which is H, not a limit of tangent hyperplanes. Okay. And so in the second stage of our we notice that X intersect H is an isis. And so it has a versal deformation. Because it's an isis, I now have a map. Let's let's put this diagram over here. So we have Cn minus 1 cross C. And I can choose coordinates so that L is just a projection on the last coordinate. And I have a map phi, which goes into C tau. And I have the versal deformation over that. And I have a map that covers that, which is equal to the identity on Cn minus 1 and phi on the last coordinate. V is equal to G inverse of 0. And so X is isomorphic to V star, pull back of V here. And these are both over C now. You can say more about this phi, and that's going to be important for our story. This contains the discriminant of PV. And then we can say that PV is a stable map, and so it has a stratification. If S contained in the discriminant is a stratum, then PV inverse of S is a Whitney equisingular family over S. So in fact, what we see is that our map phi actually goes into S bar, where the generic fiber of L is in S. This is part of the reason for only doing curved singularities for the singular set is that this map here becomes relatively simple. We only have the generic stratum, and then we have one stratum lower down, and it makes them a little bit easier to work with. We would like to repeat what we did before, but there is a problem. And the problem is that if we look at G restricted to Cn minus 1 cross S bar, then this is not smooth. And so it's not clear what we want to use for the Jacobian module of G. It's not clear. It turns out, and I guess I'm going to stop here because I'm not going to have time really to go very much further, is that what you want to do is you want to pick a convenient resolution of S bar. Let's call that R. And now we will have, if I look at the restriction of this to S bar, I will have that is certainly going to be contained in Cn minus 1 cross S bar, and we have a map onto that. And so let's call this projection R, and this projection becomes R hat. And then we look at G composed with R hat. Now this is defined in a smooth space. Because it's defined on a smooth space, we have now represented our original X as a section of a universal object. And we can apply the work of the previous section to produce invariants, which are what we need finally to add to existing invariants to give us a Whitney equisingular family. And I will stop there. Thank you.